Okay, the equation that you see here, it could be used for developing flow. Okay, but in the case where you want to use it for developing flow, you will want to use different correlation for friction factor. There's like something like correction factor for friction factor for near inlet part. Okay, that's how to open like Perry handbook or some kind of handbook. That's for, it's for both turbulent and laminar flow. Okay. So near the inlet, pressure drop per unit length is not the same compared to pressure drop per unit length away from the inlet. Okay. Because near the inlet, some energy has to be used to change the shape of the velocity profile. Later on, we don't have to change the shape of the velocity profile, right? It just looks like that, parabola shape. But near the inlet, we have to do something to change the shape of the velocity profile. So intuitively, that's caused pressure drop per unit length near the inlet to be more than pressure drop per unit length away from the inlet. And there's a need for the correction factor. Okay. So think about this. When we have flat profile near the inlet, and we want to change to parabolic profile, we need some additional energy, right? But later on, we don't have to do anything. It's just like that. In addition to changing the shape of the velocity profile, there has to be some energy dissipated to deform the fluid. So when the fluid shear against the wall, we actually deform the fluid element. Okay, that's cause a frictional pressure loss. So if we want to use this equation for developing flow, there has to be a correction factor for friction factor. All right. Can this equation be used for steady transient flow? No, not for transient flow. It is special condition for transient flow, which is when T approach infinity. Okay. If you wait long enough, pressure drop will be like this. Okay. Even though I say in the pipe, pressure drop per unit length look like that, more near the inlet, and go down, and reach a constant value. In the actual test, you may not find this because of the inlet condition. So if we have perfect inlet condition that can have it coming in just like that, okay, near the inlet can be more pressure drop. But I did a test. I have a rectangular shape. So it's like a duct like this. But inlet is just a circle shape. So I have the flow going here. And then, so what happened is fluid go into the entering point. It kind of expand to fill everywhere, right? And then it flow along the rectangle duct. So what happened is when there's an expansion at the front, I observe a pressure gain. Okay? It's like it flows slower at that point. So this means pressure drop or more pressure drop near the inlet or not is depend on inlet condition, how the inlet look like. So it's kind of more detail on that. All right. Next one, can we use it for non-Newtonian fluid? Yes, we can. And you probably did already in drilling class. To do that, we need to get the appearance viscosity, or viscosity that it seemed to be. So you may put viscosity value in it, calculate friction factor, calculate pressure drop, then calculate shear stress. Once we know the shear stress, we put that shear stress in the viscosity equation, get the new value for viscosity, then put that viscosity in here again. Do it until it converges. Okay. So that way, we know the pressure drop. Okay. So that, okay, next. Yash, right? Patel?
Yeah, yes.
Can you tell me something about non-Newtonian fluid? Who's Newton, by the way? Is it the guy under the apple tree?
Yeah.
What does non-Newtonian fluid look like?
Highly viscous. I mean, something like gel.
So, viscous fluid like honey, is that non-Newtonian or Newtonian fluid?
Yeah.
Non-Newtonian or Newtonian?
No, Newton.
I Google it, it says Newtonian fluid. Okay. So when it's high viscosity, it doesn't need to be non-Newtonian fluid. It can be Newtonian fluid. For example, honey. Okay. Something that is non-Newtonian fluid, it can be work like a elastic band. Okay. If you see it move back and forth like this, that's non-Newtonian. So this means it can store some energy and bounce back, right? So another example is like shear thinning and shear thickening, Bingham plastic. So Bingham plastic means we need a certain pressure to push it, otherwise it doesn't move. Shear thinning means when we flow faster, it becomes less viscous. Shear thickening means when we apply force or flow faster, it becomes more viscous. Hong, what is the example of shear thickening?
Like
Cornstarch, yes. Have you ever played with that?
Yeah.
So professor bring a bowl full of cornstarch solution with water. When you hit it, it won't splash. It's like you hit on the table. When you slowly push your finger in, it sinks. Okay, that's cornstarch. What about emulsion? Is that shear thinning or shear thickening? So the way I look at this is this. If we have very tiny, very fine droplet, many droplets, so that cause more surface. So when it move, it may rub against each other. So most of the time, let's think about the extreme case. If you have just one droplet of oil in water, that's not viscous, right? But if I have same volume but multiple droplets, millions of them, very fine, so it is more viscous. So this means if I turn on the pump, have it move slowly, and maybe it's not that viscous. But if I have a pump speed very high, let's say I use a centrifugal pump, it breaks the droplet, it breaks everything and mix together. It is more viscous that way. Okay? So emulsion can be shear thickening in some sense. Okay? What about flow of suspension? Certainly, so we have fluid flow with solid particle inside. Is that the shear thinning? You talk about gel, right? So gel can be like 3D network structure of solid phase. Okay. So if you flow fast, maybe it break the particle to be very small part. It will change viscosity. To know it for sure, we have to do the test. Okay. So those kind of things that if it's two phase, most of the time it's non-Newtonian. Sometimes what I experience is even though emulsion we believe that it's Newtonian fluid, but when I actually do the test, it's just Newtonian fluid. Like the one that Raymond did in the lab has a high viscosity oil and have some air inside. There's not much air inside, so it's kind of Newtonian fluid. To know for sure, we have to do the test with real meter. Okay, we already answered this, fully developed or not fully developed. So will we always have pressure gain for dV by dz less than 0 case? No, pressure can decrease where the boundary layer separation occurs. We already talked about this. Okay. For developing flow, in laminar and turbulent flow, minus dP dz close to the inlet, where z close to 0, Is that going to be greater than minus dpdz, where we are far away from the inlet? Greater mean a lot higher than 0. I said true. So in theory, pressure drop per unit length is more when we stay close to the inlet. So this is kind of detail in the multiphase flow, okay? Because single phase is also part of the multiphase flow. Okay, next, how do we calculate the friction factor? We have fanning friction formula, okay? 1 over square root f equal to minus 4 log base 10 of epsilon over d divided by 3.7 blah 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 for Reynolds number more than 4,000. Okay. Epsilon is the absolute roughness of pipe, about 50 micron, 45 micron for smooth pipe or carbon steel. Smooth pipe you may assume is 0. Okay. We have another equation, Blas's type equation, which is for smooth pipe. F equal to 0.046 Reynolds number to power minus 0.2. Okay. This is for the case of turbulent flow. For laminar flow, Reynolds number less than 2100. We use 16 over Reynolds number. Isaac, F from Coburg equation on the top and F from Blas's type equation. Let's say we have smooth pipe. Do they produce the same answer?
Both of them smooth pipe?
Smooth pipe. If I have smooth pipe, I put the number into Coburg equation. If I have smooth pipe, I have put the value into Blas's type equation. Do they give the same answer?
Yeah.
Yes. Victor, yes or no?
Should be close.
Should be close,
Yeah.
but not exact.
Not exactly.
Is it going to be exact?
It should be
Exactly the same?
pretty much close. Very, very close.
Close and the same is not the same. It's not the same.
Yeah, it should be
It's not the same and it can be far away.
Oh,
Okay, depending on Reynolds number. Most of the time, yes, it's close, but it can be far away. So, for the quick approximation, we can use Blas's type. If you want to do some serious calculation, maybe use Coburg. But Coburg is a little bit difficult to use because it is implicit equation. S equal to some function of x, or f equal to some function of f. What do we do? One way of doing it is use a fixed point iteration. Assume the value of f to be 0.001. Put 0.001 over here on the right hand side. Okay. Do the calculation and calculate this f on the left hand side. Maybe the next time we get 0.005 or something. Then put that answer into the right hand side again. Do the calculation, whatever that is. Calculate that friction factor again and keep doing this. This method is fine. It's not always converge, but in this case, yes. But it's slow. To do it a little bit faster, you may use Newton-Raphson. Newton-Raphson is similar to fixed point iteration. Okay. The difference is the formula that we use. Okay. Previously, next gas value is based on the initial gas, but we put the value into the right hand side, right? That's fixed point iteration. So look at this one. Newton-Raphson, we define function f equal to 1 over square root 4 plus something, something, something. So basically, I put everything to the right hand side, or to the same side, or everything to the left hand side. So when I put everything to the left hand side, I define the function f equal to something, 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 like this. If the f value, small f value, is a correct friction factor, if you make this equation to be 0. Okay? So now we have the equation in the form that is ready for Newton-Raphson. Newton-Raphson, we have to initiate the initial gas. We may guess the value of small f to be 0.01. Okay. Friction factor, by the way, is less than 1, right? So our initial gas should not be 10, 20, no. It won't converge. Okay. It should be something close to the answer that we think it is. So we put 0.01. The formula here is f at n plus 1. N plus 1 is the next iteration equal to f at n. So right now, f at n is all the current iteration is 0.01 minus capital F of function value and Fn divided by capital F prime on the slope value at that point. Okay. So when we do this, we will get the next value. Of course, you don't want to take the derivative of that equation because it's prone to error. So we can approximate the derivative of function by use finite difference. So derivative is function value at Fn plus epsilon minus function value at Fn and everything divided by epsilon. This will give you a fair approximation of the derivative. Right? So with this, we substitute it in function value at that point, then we get the next value. You feel comfortable with this? Isaac? Yes? Hong? No? Yes? If you haven't tried, try it. This is, I use Excel to get this. This is the value that you should get. Okay? Or you may don't try it and you may try it in homework. If it's not in the homework, maybe you try it in take-home exam. I cannot put something like this in the exam, it doesn't fit, but okay, I think you can do it in take-home exam, if any. So this is an example for you to try. I put Reynolds number 10 to the power 5, diameter of 2 inch, 0.052, epsilon 150 micrometer. This is a galvanized steel. Oh, by the way, how do you get the value of roughness? Where do you get it from? What? Table. Where do you get that table?
Experiments.
What?
They have to put the experiments in the power.
Ah, okay. In short, you Google it. Okay, it's in engineering toolbox. They will tell you the value. Sometimes there's a table, yes. Sometimes they put this in feet. We have to convert everything in the same unit. This means if I put 150 into that equation, doesn't work. It has to be 0.00015. Got it? Everything has to be same unit, SI, okay, meter. Alright, if you try this function value, you will stop when the answer repeat itself. Okay, so in this case, I get 0.006805. Try it. If you get something else, tell me. Maybe I'm wrong, but previous student check it for me already, and I think it's correct. Okay, successive method is the one that you can do with calculator. This calculator. Okay, how do you type it? You put 0.01 and put the equal sign, okay, or exe over there. 1 exp5. This is to do 10 to the power 5, and put the arrow on this calculator. There's an arrow, and you put capital R over there. So this is just tell you how to actually put it in the calculator. Okay, 0.052, put it in D. 150 exp minus 5, put it in E. Some calculator doesn't have this syntax. Okay, but what it is we try to make the equation, and then we type everything on the right hand side. Okay, let me remove that. So you will see that I try to make it in the form like F equal to something of F. So that's why I take the power of minus 2. So when I type everything, this part is equivalent to that, to the power of 2 and exe. I just press several times. Okay, notice that I put ANS in the square root. So it produce answer and use answer again, reuse it. So I get function f friction factor value, whatever friction factor value that become ANS. So you need to have ANS button in the calculator. You put it in here and you do it several times. So if you have problem, I think you should be able to do this. If you have problem, come see me. Okay. Then you get the answer. Okay. Let's do something a little bit different. This one is about single phase heat transfer. So previously we talked about pressure drop, right? The case where heat transfer is a concern for multi-phase flow and single-phase flow is subsea pipeline. We may just say, hey, insulate the pipe. How much? How do we insulate the pipe? Okay. How thick is the insulation layer thickness? If we put too much, it's expensive. If we don't put enough, we don't have insulation. So we have to do calculation for the heat loss. Okay. So this is for the case of subsea pipeline. For heat transfer calculation, I will give you first example. This example is to show you that whenever we have heat transfer, most of the time, the energy from the heat transfer term is a dominant term. The rest, the change in the V square or gravity term doesn't matter. Okay? You haven't seen the equation yet. Let me go through this equation. If there is a direct source or sink of heat, kinetic and gravitational energy can be neglected. Okay. Let's do energy balance, D form. D form of energy balance can be, for a steady state, can be written like this. dE, or total energy, equal to dQ. The change in the total energy equal to the change in the heat added to the system plus the work added to the system or work done on the system. Think about it like this. If we do some work on the system, we add some heat to the system energy go up. Right? Make sense? And what is exactly is the system energy? System energy consists of kinetic energy, gravitational potential, enthalpy. Okay. Enthalpy means hot or not hot. You may think about it like that. But from thermodynamic class, you may have a precise expression, which is the H hat equal to Cp hat dt plus V hat is 1 over rho, minus T dV hat by dt at P, constant P, and everything dP. So that's a thermodynamic definition of enthalpy. Okay. So this means when the temperature change, hey, V square doesn't change, GDH doesn't change, but enthalpy change. Right? Okay. So that's the dE. We put them together, substitute it in. So left hand side is dE. What about right hand side? Right hand side, I keep the W hat over there, but dQ hat, I change it to U pi d T infinity minus T over m dot dz. So this term is about heat transfer at the interface. If I write it like this, look at this one. I assume GDH is positive, going up. Cp dt positive, temperature go up. So if temperature go up, temperature multiplied by Cp is positive value, right? So dt, when temperature increase, dt is positive. So when I write it like this means heat is added to the system. And this term I use T infinity minus T means that, okay, environment is hotter than the system. So heat is being added to the system. If you check, each term is positive. Okay. Yeah. In the case where T infinity is less than T, or we lose heat. When we lose heat, this term becomes negative. And it will imply that temperature has to drop. Yes?
So, the work done on the system, is it positive? Because they got work done on the system.
What is work done on the system? If I punch water, is that work done on the system?
Yeah.
Kind of.
Yeah.
So if I turn on the pump, That's work done on the system.
Okay.
Work done on the system is positive in this definition. So if I have a shaft work, like a pump, work done on the system, that's positive, right? So when I put the work in the system, energy of the system go up. So let's say I put the work in the system, I turn on the pump. I turn on the pump, it moves faster. So work done on the system is positive in this definition. You can define it differently. If you define it differently, you just have to put dW to another side. Will become work done by the system. Work done by the system, for example, compressor, maybe. No, not the compressor, what would be? Turbine, yes. So when it's expand and push against something, that's work done by the system. Alright, you may notice that I use everything SI, okay, so that the unit is consistent. Typically energy is what? Half mv squared, right? But this thing I divided everything by m dot. So look at this one, look at the unit. H hat is joule per kilogram. That's H hat. Q hat is joule per kilogram. Work done is joule per kilogram. In the pipe is 0 because we don't have pipe pump in the pipe. So there's work done on the system. Okay. Cp joule per kilogram per Kelvin. When I write it like this, think about it like when you do that in Excel. So joule is on the top, kilogram is on the bottom, Kelvin also on the bottom. Okay, joule per kilogram per Kelvin. Joule per kilogram per Kelvin multiplied by Kelvin becomes joule per kilogram. So every term has a unit of joule per kilogram. So we do energy balance in the sense of joule per kilogram. Look at m dot. M dot is a mass flow rate. Okay, kilogram per second. Okay, V hat is specific volume of 1 over rho, cubic meter per kilogram. U, overall heat transfer coefficient, watt per meter square per Kelvin. Watt is joule per second, right? So when we work out the unit, joule per second, and this one is kilogram per second and per second cancel each other. So V joule per kilogram and cubic meter, square meter per Kelvin is this term. Small d and z, dz is, so that d and that d is not the same thing, okay? That d is the diameter, inner diameter, but dz is a infinitesimal change of the axial direction. So dz is a length. So this and that become d square and delta t is Kelvin. So every term is joule per kilogram. By doing this, we say, hey, this is the form of total energy balance. Okay. Let's try to show you how energy balance works for single phase flow. This course doesn't cover for the case of two phase, but you may be able to do it if you can do single phase flow. For example, if you happen to have to do for two phase flow, you may use mixture specific capacity, heat capacity. You may use mixture density as a role or something like that. Okay, that's the term that we want to focus. This thing a little bit strange. The first term is okay, right? Delta P over rho is okay. Delta P over rho, that is like Bernoulli equation, right? Delta P over rho. So it's okay. But the second term is maybe new for you. So the second term go to 0 for ideal gas. Okay? The second term actually go to 0 for ideal gas. And maybe we show that to you later. Okay, now let's talk about the example of heat transfer for single phase flow class. Okay. So after we finish single phase flow heat transfer, then we will do two phase. Okay. This is an example from Burst George Lightfoot, page 459. Look at this one. We have flow from the bottom through heat exchanger. Okay. It's kind of pipe-in-pipe heat exchanger. We have flow coming in at 100 feet per second, 200 pounds per hour. Okay, but why do I have to tell both of them? One of them is like mass flow rate, one of them is velocity. Isn't it interchangeable? We can use one instead of another? No. Okay. Unless we know pipe diameter, we know density or something. And it's coming in at 300 Fahrenheit, 30 psia. Okay. It's coming out, so it's coming in hot. Okay. It's coming out at 0 F. Very cold. Okay. 0 F. And it's coming out at some velocity, I don't know what. Okay. But it has the same mass flow rate. And the pressure drop from 30 to 15. I put question mark over there for the velocity. Why is that? Why don't we know the velocity? Does it change? So look at this. This is the dry air. Right? So when temperature change, will density change? When the temperature go down, it shrink. Right? So to maintain the same mass flow rate, the volumetric flow rate may not be the same. All right, the given information is the formula for specific heat for dry air. That's a formula, and temperature has to be put in Rankine unit. Okay. Cp tilde is in BTU per pound mole per Rankine, and temperature over there is T in Rankine. Rankine minus 459.67 become Fahrenheit. That's just a conversion formula. Alright, now we want to calculate the rate of energy removal across the tube wall. How much do we have to remove the energy to have that 300 Fahrenheit temperature drop? Do we have to remove a lot of temperature? Okay, let's take a look. Basically, we use this formula that we already derived. Put the value in and done. So this formula is actually equivalent to battery equation, right? But a little bit more detail. Okay. So dry air, we have work done on the system equal to 0. We don't have pump inside. Okay. dH is Cp dt plus V hat minus T partial derivative of V hat over T at constant pressure, and everything integrate with respect to pressure from condition 1 to condition 2. Okay. So we integrate it. We have half V square over V2 square minus V1 square. That's the energy gain, that's the chain of energy for the kinetic term, potential term, and enthalpy term. And that's the heat. Okay. Heat added to the system. If our answer becomes negative, this means we remove heat from the system. Okay. Is it going to be negative? Maybe. Now let's take a look at this. How do we calculate V2 square minus V1 square? We look at rho 1 V1 equal to rho 2 V2. Constant mass flow rate. Okay. Rho 1 V1 equal to rho 2 V2. So m dot is constant. From this, we also know that PV over Tn equal to PV equal to Tn. This is for the case where compressibility factor or Z equal to 1. PV equal to Z N R T, right? And we put N and T at the bottom. We have PV over NT equal to PV over NT. It has to be the case. Okay? We assume ideal gas. Okay? Or we have V over N equal to molecular weight over rho. Okay? This is actually come from the ideal gas. What is the molecular weight of dry air? 29, 28? About 29. Okay. So V over N is molecular weight over rho. Alright. Then we substitute it in. We have P1 over T1 rho 1 equal to P2 over T2 rho 2. Do a little bit of math. Then we get the ratio of density is related to the ratio of velocity and related to the ratio of pressure and temperature like that. Okay. Then we substitute it in, get the value. Okay. It's about 2000 something. That's the kinetic term. For potential term and heat term, we'll go through it next time. Okay. Today's time's up. It's 12:20. All right. So the time is up. It's 12:20. See you next time. All right. Next time is Thursday. Thank you for coming. Goodbye.